and how we can find the solution of this type of equations. And we take one example is the elliptic equations, and after that we take parabolic equations and how we can distinguish between them. Usually we have two classes or three classes of the partial differential equations. Elliptic equation, an example of the elliptic equation is the Laplace equation. The Laplace equation is represented by steady state case where the derivative of time with derivative with respect of time does not appear here. There is no derivative with respect to time. We have also parabolic equations or type of PDF equations, and we can represent this as example using heat transfer or heat conduction equation. And here we have one derivative with respect to time and one derivative with respect to space. Second derivative with respect to space. The third class is the hyperbolic equation. An example of this is the wave equation, as we said. After that, we talk about the classification, how we can classify the equation using the general formula. So this is the general formula. We have uxx. That means this is u, second derivative of u with respect to x squared. This is a like this one. We have here b du square. We have here dx dy. Okay, so after that we have c du square over dy square, and after that we have the constant equals 0. So by knowing this constant a, b, c, and d, we can determine the class of the ODE equation. Otherwise it is elliptic, parabolic, or hyperbolic. Okay, so if the quadratic is negative, so this is elliptic, like Laplace. If it is equal 0, so this is parabolic. If it is greater than 0, so in this case this is hyperbolic type. So after that we take example using the elliptic equation and the Laplace equation, and we talk about how we solve this heat transfer by using finite difference solution to the elliptic equation. And we take the grades here to represent the heat plate. If we have here any node, if we are, our interest is to compute the temperature at any node. So here we have heat transfer in this direction. Okay, heat transfer in this direction. And in this case, we represent this by the coulombs. We start from Qy and then Qy plus delta y. And also we have heat transfer in this direction. So if we know the point, if we know the value at this point, and we know the point at, for example, I plus 1. So in this case, we have here, for example, this is at G, and here at J plus 1. So in this case, we can use finite difference, eitherwise central finite difference or a forward finite difference or backward finite difference to present the equation transfer at this node. And after that, we talk about the equation of the Fourier heat conduction equation, like for example Laplace and Poisson's equations. And here, what's the difference in Laplace? In the Laplace, we have f of x, y, and this is represent the source of the heat is equal 0. This is what we have. After that, we take the Laplace as example, and we use the techniques or the finite difference technique to represent the second order derivative or the second order equation, the PDF equation, by using central divided difference. And here we have delta x represent the step size in the rows. We have delta y represent the step size in the columns. So after that, we finalize with the two equations, one horizontal and other vertical equations. And to simplify this one, we assume delta x equal delta y and this equal h. So if we have delta x equal delta y and equal h, so in this case, if we multiply both sides by h, so we cancel this term. These terms are common between the two equations. We can combine them because these two terms represent the node, the interesting node that we want to compute temperature on. So after that, we can rewrite the equation. So we have this algebraic equation in terms of the node that we want to compute the temperature on and 4 nodes around this node. So any heat plate, we can represent this plate by a grid, and this grid consists of different points inside, while the temperature at the boundaries should be given. This is constant temperature here. Given temperature for us, we have some temperature given at the boundaries. So by knowing, if you want to compute this one, we can use 4 points around it. One point, for example, forward in the x-axis or y-axis, and 1 point backward. And also we have in the columns the same, one below and one above. So this is the technique that we use. So this is formula that we use. This is the equation that we use, and this the temperature here is given at the columns. We have here column 0 at this point, and here we have columns given, and here temperature is given, and here is given. So at any node, if you start from node number 1, for example, I1, J1. Okay, so this is node number 1, 1, 1. So we can rewrite the equation for node number 1. So here we just substitute instead of I by 1. So you have here T21 plus T01 plus T12 plus T10 minus 4 T11 equals 0. After that, we look for these terms that contain zeros. Here, this that contains zeros. This will be constants. Okay, here we have some, this is constant, and some points also we have it here at the boundary. For example, here you have T4. Okay, for 1, you have here this also constant. You have here T4, this is for this column number 4. Sorry, 4, 3. Or 2, sorry, and this is T4, 3. This also constant. Okay, and here we have the number of the rows. This row 4. Okay, but column, so we have T1, 4, and here we have T 2, 4, and here we have T 3, 4. Okay, so this is represent the rows. Okay, so this is given. All these points are 100, and these are 50, and this is are 75 degree, and these zeros. So after that, we apply this equation on all the nodes here inside this plate. After that, we get this matrix of equations. If we get this matrix of equation, it is easy after that by using it's not actually easy. It's dependent on the number of the nodes. If we have here, for example, 3 by 3, in this case, we have 9 equations. So in this case, you need to solve these 9 equations by using any techniques, elimination techniques. If it is 2 by 2, you will get 4 equations. So a little bit easy. But if we talk about 20 equation or 20 point or 10 points. So 10 point, you need 100 equations. So this is a waste of time and waste of the RAMs of the computers if you use to complete this one. So this is another example that we did the last lecture. I talk about the temperature, how we can compute this one, and after that we built the matrix, and then we solve this one using any elimination techniques. So to avoid these huge computations for large grades, because usually we can have large grades from 20 nodes to 20 nodes or 100 nodes, 100 nodes. So in this case, you can expect how many equations that you need to solve. To avoid this problem, we can use Gauss-Seidel method or Lippmann method. And this method solves the problem directly by using some assumptions without the need of this difficulty. So here what we have the equation. This is the equation. We rewrite the equation here for the temperature, and we take the average of the temperature at the sub-rounding nodes. So this is our interest, is to compute the temperature at Tij, and we take the average of sub-rounding nodes around it, the 4 nodes over 4. After that, we use over-relaxing method, this over-relaxing equation, to update the equation. So here we have the new value of the temperature. It's equal the new that we computed here, multiplied by lambda. Lambda is a coefficient or factor, weighting factor. Usually it is value between 1 and 2. Sometimes we selected 1, 1.5, 1.4, 1.3, like this one, up to 2. Plus 1 minus lambda multiplied by the old value. So this is the old value. Usually we start with the initial value that we have. In this method, we assume all the initial values or the temperature Tij initially are zeros. All the values Tji's initially are zeros. So this is the idea. We start from zeros. After that, we iterate. So we complete the iteration until we stop. Where's the stopping criteria? We stop when the error is false below a predefined stopping criteria. So let's try this example and see this example what we did last lecture. So here, for example, we can use these equations for Gaussian equation. Okay, so here we have the temperature at T11. So here you can see we assume all the temperature here inside this plate are zeros. These temperature are zeros now at the first condition. The values of the temperature are zeros. So to compute T11, so you can see what sub around we have here 0 and this 0 and this also 0 here and this 75. So we have these 4 nodes. We have 0 here, 0 here, 0 here, and 0 here. So we have 75 over 4. After that, we go to the second node. Or we need to update this before we go to the second node. We need to update this value by using relaxant or over-relaxant method. So over-relaxant method, it's equal lambda. Lambda in this question is given equal 1.5. So we take lambda multiplied by the value, the new value that we compute here, it's equal 18.75 plus 1 minus lambda multiplied by the old value. The old value is 0. The old value, because we assume the value, the old one is 0. So this is 0. So in this case, the relaxant value of T11 is 28.125. After that, we can go for this node, this second node here, T12. Okay, T12, we take this one. This is 0, and this 0, this 0, and this one we already computed is 22.125. So we have 0, 22.125 plus 0 plus 0 over 4. We take them. After that, we use the relaxant or over-relaxant. This is lambda. This is the value, the new value. plus 1 minus 1.5 it's lambda multiplied by the old value is 0. So we do the same things for these nodes. After that, we update. When we update these things, after that we do for all the equations for all the nodes, and then we update the values to this one. So now the next step, we do the same things. We start again, but now with the new initial condition, not zeros. So this is the initial for the next step, or the value for the next step. So now we can do the second iteration by using these values, and the result in the second iteration will be more accurate. So we do it the same iteration until the value of the error, percentage relative error, falls below the predefined value, which is 1%. So we need also the third iteration. When we get the third iteration, so in this case, the maximum error here is 0.71, and which falls below the pre-specified error. So as a result, this will be the grades inside for the inner nodes. So this is the second method that we talk about in the previous lecture, how we can solve Laplace equation using two methods. What we have today went also to talk, sometimes we don't have only, sometimes we have another parameter. So here we are interested to compute the temperature. What about if we are interested to compute another variable, not the temperature? So what we studied before, we are interested to compute the temperature. Our interest is to compute temperature, but sometimes also we need to compute secondary variables, not the temperature. Okay, so how we solve these types of equations? So for the heat plate, usually the secondary variable is the heat flux. Okay, so in the heat plate, the secondary variable is the heat or the rate of the heat flux across the plate surface. And the equation of this heat flux is given by this one. This is the equation for heat flux. So at any node, we want to find the direction of this flux and the moment of this flux, the value of this flux. How we can do this one? So this is a vector, so we have the value at x and we have the value at y. After that, we need to determine the value of this flux. Okay, otherwise, in this direction, the heat transfer in this direction or transfer in this direction. So we want to know the direction of this flux of the heat. So this is the equation of the heat flux or rate change of heat flux, and the direction is given by Qi, and Qi or Qn is equal the root square of Qx square plus y plus Qy square. And here we use a center divided difference, you can see, to represent this one. K bar is the coefficient of the terminal, P is the density, C is the heat capacity of the metal, T is the temperature. So what we want to know, the value of Qx, and after that the value of Qy, to determine the value of the flux or the density of the flux. And then we need also to know the direction of this flux. Otherwise, the temperature will transfer in above or below. What will be the direction or the angle of transfer of this flux? So here, by knowing these values of temperature at these nodes, if we have this node here, so we need to have this node before it in y-axis, and also this node before it in y-axis or x-axis. Okay, so we use these two nodes to determine Qx, and after that we have here in y two nodes also. This node will be here, and this node is here, and this is the node that we want to find. So by computing Qy and Qx, we can determine these quantities Qn and theta. So if we use the table, what we computed in the previous example, here to determine the distribution of the heat flux for the heated plate. If you assume the plate is 40 by 40 centimeter, and it is made of aluminum, so K bar here is equal 0.89. So we know this Qx is equal minus K bar. Okay. So here, if we talk about node 1, 1. Okay, node 1, 1. So at node 1, 1, this is the node 1, 1. So by using the data we computed in previous example, you can see this is TI1. The TI1 is the point before, at this here. That comes at this point. The point here at the boundaries is 75. And Ti plus 1j, so this is 2, 1, so this one, so this will be the value. And this is equal 33.29755, because this is approximated. Okay, so this is approximated in the table. It's actually 33.295755. So here we round it off to become 33.3. Okay, so we use both, and we have delta x 2 multiplied by delta x. X is 10 centimeter. So we multiply this one, and we compute the value of Qx. A second, to compute Qy. So Qy here, we have one heat before. This is what we have. So this is the temperature here is 63.21. So this is the temperature above. And we need the temperature at this point is 0. Okay, temperature here is 0. This multiplied by K bar over to delta Y, and delta Y also it's equal 10. So we have here 20 centimeter. So, and this will be the value of Qy. Okay, so we can do it for all the nodes. For all the nodes, we want to determine the direction of the heat transfer. So we do it here only for 1, 1. So we can do it for all the nodes. Okay, we can do it for node 2, 1. We can do it for node 3, 1, and like this one. So step by step, we can determine the direction of the flux for all the nodes. So the flux now, it can be computed by compute Qn. So Qn is equal this root square of 1.022 square plus minus 1.549 square, and this equal 1.856. Okay, so this is the value of the flux, or the density of the flux. So also we can use here, for example, to compute the direction here of it is the trajectory. So this equal Qx or Qy over Qx by take the tangent inverse. Okay, and this equal minus 56.584 degree. So as a result from this one, we can summary that this flux is directed down to the right. And values for other points also we can compute. We can compute also for this node, and we can compute, we determine the direction of the flux for this node, for all the nodes, to know to which direction the temperature will transfer. Because theoretically we know the temperature is transferred from hot body to cold body, because this is large with compared to this one. So you can see the temperature goes with angle to zeros because this is cold body. And this is the most hot side or boundaries. Okay, so we can do it. You can try to compute, for example, for this node and for this node, just a practice, because here in the example we have it for only for one node. You can try it for 2 or 3. Any question up to here? Okay. So also the heat conduction equation can also consider the moment of heat stored in an element over a unit of time. If you want also to compute, for example, or to consider the moment of heat stored in an element, for example, over a period of time. So how we can do this one? Also, we can do it depending on how many interesting variables that we want to compute. Okay. And this is the equation that represent the heat stored in an element. Another important topics usually is the explicit method and implicit method, and this is another method that's used to solve the ODE equations. The explicit method usually we use the temperature at time n+1 dependent explicitly on time n. So we need to compute the temperature at time here at time n. We compute the time n+1 using the temperature at time n. So a previous time. And this is the equation you can see here. So here we have the temperature at time. We need to compute the temperature or to predict the value at the previous time or future time at t or i+1. That means it's the time, next time, by using information of the temperature at the previous time or the current time. So this is the difference between them and the implicit method. The implicit method, you can see here. So here, the second derivative, you can see we use it here to compute the temperature. The temperature here at T, for example, +1 by using information at the same time. And also, this will be clear here for the second derivative. In the second derivative, we use temperature at I+1 to compute the second derivative in terms of space, while here in the explicit method, we compute the derivative in terms of the current space, or the current time, or not the previous time. But if talk about which is robust, implicit will be the most robust because usually implicit method stable, usually unconditional stable. The explicit method sometimes is unstable. Although explicit is easy to compute, because the advantage of explicit method is when we use finite difference are sample and computationally faster. And we can use and compute and the explicit here. Usually we use a central divided difference and forward. Here we can use central divided difference, and here we can use forward a divided difference. This is difference a little bit from implicit method. We use center, divided difference, and backward divided difference. Okay, so I think I will shift this to next class. We have two methods, and just we want to review them. And next week, inshallah, we'll review this method, this sample method, in Sunday. And after that, we can finish this topic, and then we can have otherwise